I will start my presentation with a brief background on the aims of the Firecaster project. So to then go through the introduction to the Firecaster field description system and its parametrization, and a little bit of discussion. So the aim of the Firecaster project, we've seen several presentations, and we are going to see more presentations, was to develop a wildfire decision support system to provide operational agencies more efficient ways to forecast fire danger. And to develop these tools, a key element was the vegetation, but consider it as fuel. And why? Because we need information about fuel to run fire spread models, which are used to calculate, to run risk models, and so the primary question was, okay, we need information, but which data we need, which parameters, at which scale, which frequency, and which structure, how we are going to store all this data. So if we take a look at what has already been done for describing vegetation, we can see that the way fuel is described depends on which is the intended application. It's just fire behavior, fire management, or which are the available resources to characterize this vegetation, and at which scale we want to work. On the other hand, we have the requirements of the Firecaster project. We have seen the presentation of Patty this morning that this is a very flexible system. So the vegetation parameters should be able to match several fire behavior models, and the system should be able to integrate data from several sources and work at several scales. So in order to, to answer to all of these points, we developed the Firecaster field description system, which is an integrative and evolving data structure for fuel. It was based on mainly on existing fuel classification and description systems, and it considers the more important fuel input parameters of current fire behavior models. So here we have the big picture of this system and how it's connected, I would say, to several data sources, to a land surface model, and then how we can connect to different fire behavior models. And today I'm going to present how this parametrization that was carried out using already available data in order to provide a set of field attributes for fire spread modeling, which can capture the spatial variability of vegetation. So what's the Firecaster field description system is sort of, as I said, data structure, and we have modeled a vegetation stand considering that it's composed by several structurally distinct pseudo-homogeneous and georeferenced field layers. And this description is adapted for a resolution scale from 50 meters to 5 meters. Why this layering approach? This is common for describing vegetation because it can be linked the different layers to different fire behaviors and fire descriptors. So in turn, each field layer is composed by field elements and field elements by field particles. So we define a series of field layer attributes which are time dependent, so they evolve over time and depend on the position on the space. But we can, since the system is flexible, we can add more variables if we have the data. And in the same way, we selected a series of attributes for field elements and particles. So, as I said, the core of this work was develop the methods to obtain a set and the values of this set of field attributes based on already available data, and it was implemented for the Corsica region because this is the region of test of all the tools developed in the framework of this project. So here we have the different processes, steps followed to get this parametrization. So first step was the field classification and mapping. So for this purpose, we use the French reference GIS database, which describes forest and natural vegetation stands of at least a surface of 0.5 hectares. This database is commonly used by foresters and land managers, and the characterization is made using a soil cover approach. So we have sort of different levels of information, the soil cover, then we go to information on the stand density, then we have the general composition, and in some cases we have also information on the tree dominant species. So for the case of Corsica, that means that we have 58 stand types. So before just getting all these types and going through, we perform an analysis of a surface area distribution analysis to see if we can see some types that were not important or not significant. So we just give a threshold value of a surface area, and if the surface area of a certain type of stand was less than this threshold value, we take a look at the fire risk associated to this stand type, and then we decided to keep it or to go to something closer and to reduce a little bit the number of stand types. Moreover, we perform a relevance analysis because, as I said, we have sometimes a general description. So, okay, we have a closed forest, deciduous forest, but if we have to, do this layering approach, it's quite difficult. So we assimilate this type of general forest to the more typical observed in Corsica. And for a special case of shrublands, the shrublands occupy a very important surface of the Corsica island in terms of vegetation. And we decided to split this type in 3 types according to the difference observed by bioclimatic stages. So depending on the altitude, there are very different vegetation structures. And that allow us to have all the classes vegetation or vegetation stand types. Of course, for running simulations of fire spread, we don't have only vegetation, we have cities, we have rivers, and so on. So we use also the core inland cover to fill not forested areas, sort of stacking all the layers. So next step was going through the definition of layers per stand type. So we have sort of a general description as closed forest of pinus species. So we have to figure out how it looks like, this type of forest, to model, to split this forest in layers. So we need quite a detailed data to do this process. That's why we choose to use the National Forest Inventory Field Surveys, which these are national surveys to assess the state of forest in terms of both botanical and ecological resources. So during these surveys, we have a grid. All the territory is there are a grid of plots, I would say, in the territory, and they are every 5 years we perform measurements in this sort of plots, which is a circular plot of 4 nested, I would say, plots inside, and we have general information of the forest stand descriptors, where the the different species present and very well characterization of the trees. So for instance, here we have several variables that we can find on the data. So we have tree species, several measurements, and what's important is to see the characterization in terms of the forest cover. We have this sort of, we have information about the herbaceous cover, the ligneous cover, depending on if they are lower than 2 meters or higher than 2 meters. And we also have this 3 species information. So based on this particular data, we identified in a certain way general types of layers. So for describing a typical forest, so litter, the herbaceous, the shrubs were divided depending on this threshold of 2 meters, and then the trees. However, it's important to note that lower shrubs less than 2 meters, it's not a layer itself, because this layer can be, this strata can be formed of several species, and each species has different structural characteristics and chemical characteristics. So the layers itself will be, for example, herbaceous species 1, for low shrub we will have species 1, species 2, and so on. So to do this, for each stand type associate these sort of layers which are present or not, we follow several steps. First of all, it was necessary to link the sampling points of the forest inventory with the stand types in the identified and modified of the DB Forêt. And since it can be a delay of time between the sampling performed by the forest inventory and the images, sometimes there are differences, and also the information of the point position of the sampling point, maybe it's not accurate, and it's the center of the grid, but not exactly where the sampling plot has been centered. We observe that, for example, in this case, we have the sampling point in the black dot, which the information we have is that it's a closed forest, and we have certain species. And if we take a look at what says the GIS data, we see that in blue, it's an open forest, not a closed forest. But if we take a look just the green, so next is it corresponds exactly to what we have. So we just perform an algorithm to be sure that we make the good correspondences between points and stand types. So from this, so then for each stand type and the corresponding points, we wanted to assess the variability of a same type of forest, of a closed forest of certain pinus species, to be sure that we can give a mean value, I would say. So we compute the statistic estimates for the surface cover Perez strata as given in the forest inventory, also for the tree canopy, and the modified brown blanket cover scale, which is a scale that between 1 and 5 that gives us information on the presence on the cover of all the floristic species. So here we computed estimates, but here we have it's easier to see it in a graph. It's more friendly. So we have, for example, the surface cover of the different for all the points, inventory points for one stand type. We can see that we can really see the tendency of which is the percentage cover of herbaceous or a certain type. And we did the same for the tree species and for the different species, all strata considered. So from this analysis, we could then obtain sort of these layers. So we have, for example, a closed forest of a typical Corsican pine, and we have that, for example, in the overstory. So we have two type of trees. Then we have no intermediate understory, and we have just lower shrubs and herbaceous and litter. Even though still a step was necessary, final steps, to complete the data and to validate. Why? Because we don't have enough points for all the stand types. So the statistical analysis allowed us also to see the relevance of the number of points and the significance. So it was necessary to, sometimes we don't have no point. So for instance, shrublands, they are not point inventories. So, and other ones, the number of points, it was so low to be sure that the data was significant. So we should do some field observations and also use other information on vegetation to be sure that the definition of layer was correct. So then, once we have the layers, we have to put the data inside. So we have different types of layers. What's more concerning surface vegetation, it's patchy vegetation. And unfortunately, we don't have found data on the literature concerning the size of this patch or of vegetation. So we have considered that vegetation is homogeneously distributed. And on the contrary, for rice vegetation, so low shrubs, high shrubs, and all trees, we can found correlations for the shape and for the size of these elements. So for instance, we have here the field layers attributes considered and how they have obtained. So for the surface cover was mainly the forest surveys, forest inventory surveys. And for the layer-based height, for the litter and the grass, just definition is at the soil level. And then we have used allometric equations for rice vegetations and so on. You see it's almost the same for the layer top height. Concerning the layer density, the number of elements per hectare, as I said, we've done a strong hypothesis, but we don't have data to better improve this definition. So, and for the rice vegetation, we use our information of the field elements to go back to the layer, compute the layer density. The same for the fuel load, and the water load was estimated from the literature. Of course, from values relevant for the fire season. So here is just a scheme to show you the interactions between how have been computed the field element attributes and the interactions between them to obtain one and another. And this is just an example of how surface cover was computed. So we think we have data and it's so easy, but we have to be coherent. I don't know the word in English. It has to match the different measurements have to match. So we have to go back and validate that was right the different values that we considered. Concerning the field particle attributes, we just take a look at the literature that there's an extent database concerning the particles attributes commonly used for fire behavior models. So it's an ongoing work, the evaluation of this parametrization against current field parametrizations for the radar model. So the connection of all this data to what's needed for the radar model has been done, and we are just trying to evaluate how good is this detailed description. Of course, another issue is, can we extend these methodologies to to a national scale or even beyond? So, of course, the GIS reference database and the field surveys are at national scale, so we have these data sources. But still, there's a work, because that depends on the number of sampling points that we have for each type. So maybe there's a field work to complete this database. At the European level, the forest inventories are more and more used. So there's also from 2010 there's it's been a framework to be in accordance all the countries to have the same, I would measure the same parameters. So that could be interesting. And we have made strong hypotheses to have this parametrization, but we can improve, still we can improve it. We can add the body fuel because there's also information on the national inventory surveys. We can try to be more precise describing the differences in the territory for the same type of stand type, considering the aspect or the altitude. And to finish this presentation, I want to talk a little bit of this part of the system, which was the coupling with the land surface model surface. And this work was carried out in collaboration with the CNRM, avec Valérie Masson and Patrick Lemoigne. And we try to explore how to determine the dead fuel moisture content, the live fuel moisture content, and the fuel load by using a land surface model. Because if we want, as Adam said all along his presentations, if we want to predict, we have to predict also the state of vegetation. And that's the good point of using a land surface model. So for the fuel moisture content, the problem is that we don't have data for the validation. So it was implemented the fine fuel moisture code, which gives us an insight of the fuel moisture content, and it was implemented at operational scale every 10 minutes by Ronan, which is here. Then we also, for the live fuel moisture simulation content, we assess the capabilities of this model by comparing several diagnostic prognostic variables of the model with a database of measurements of live fuel moisture content. The results were promising, but still more work is needed. And also we explore the possibility of have daily live vegetation and litter information of the fuel load. So this work is, it was just exploratory, and it will be hopefully a PhD at CNRM, which will continue this work. So thank you. If you have questions.